All right. Well, thank you again for that welcome, and it's really my pleasure to speak to you all today. And we've had some really great talks this morning, and so I'll kind of try to focus on some of the things that are different. And it's interesting when we look at some of the themes that are already emerging, like a lot of this uplink, right? So when you look at how's 6G going to be differentiated, I was just talking to Peter Asbeck on RF, power amplifier design, and you really kind of understand the constraints of wireless devices. And it's interesting when you look at theoretical analysis versus the practical world. As engineers, there really is the constraints that make our work interesting, right? So you can make something better, something else gets worse, and it's that multidimensional optimization. And I think as we're looking today in a lot of these sessions on physical AI, personal AI, and kind of bridging the connectivity, the computing, the sensing, all these different requirements, it really requires us to open our minds as engineers. And I think that's what's kind of great about this CWC event, is it kind of enables these academic industry dialogues on, sometimes people think, oh my God, I have this amazing cell phone, wireless must be kind of slowing down and there's not a lot of innovation left. And yet if you're in industry, you're like, oh my God, there's so many things that are so hard, so many interesting problems that are challenging and that are multidimensional, where you need fresh new perspectives. And at the same time, that core aspect on how are we able to make things better, what are the KPIs we're driving to. And so it is an interesting one too, where that kind of expanse of different types of devices, they all bring their own unique aspects. A lot of discussions this morning on the different data rate requirements of different devices, the requirements as we're putting all those things together. And so we were kind of tasked internally at Qualcomm maybe about 6 months ago. Our CEO, who's in Davos this week talking about 6G and other topics, we wanted to have one slide a little bit that kind of shows that expanding surface area of wireless communication. So hence we have this wonderful cone. And it's always interesting when we look back to look forward. So I joined Qualcomm in 2000, right when EVDO was being worked on. We were bringing data into cellular. It was kind of an exciting time with Roberto Padovani and many others. And we kind of had this challenge of trying to get to a couple megabits per second. So I always remember 2.4 megabits per second and 1.25 megahertz of bandwidth. And we're trying to do 16 QAM, and we had phase noise, and we needed to do adaptive equalization. And we even had projects called multiple antenna receivers. Like, oh my God, you're gonna have more than one? Yeah, you're gonna have two. Wow. And of course, now we have MIMO and things like FWA. We're talking about how to go from 6 to 8 antennas on the device. But the other point that's interesting is, you look at the bigger changes going on in how we use technology. So there's kind of always a supply side and a demand side. That is supply side of what is technology that is evolving, that is getting better, and kind of the demand side of how do we put it together and solve a pragmatically useful, commercially useful problem, right? We're not in the business of creating a paper specification. We're in the business of helping enable this communications and compute and open up these new applications. And that's when we start then looking at this aspect of, cloud and big data. And we start looking at things like augmented and virtual reality. And then we start looking at things like humanoid robotics. And absolutely, these things will have Wi-Fi, but they're also going to be cellular connected in many instances. And we go back to QoS. I remember a talk from Misha, back in I think it might have been 2014. And we were talking about, SLAs and the requirements even, where does Wi-Fi fail and you need to use 5G. And then we start thinking a little bit on these new types of opportunities. We had that discussion from Chad on connected drones. And so as we look towards the 6G, we really are seeing a huge number of different types of use cases and different technologies coming together. And so it's this kind of perspective of how is the technology itself improving? What are the applications that are improving? And then what are the use cases we're shooting for, recognizing that the world is getting a bigger place. Things are getting more and more devices connected. So this is our kind of one slide view on how all that fits together. And then it kind of brings us back to these perspectives. What are the priorities? And then also, how does communications and compute intertwine? And I think that's partly this big picture aspect of the way we use devices is always changing. And there's a famous quote in Great Gatsby when they say, how does someone get poor and go bankrupt? The answer is slowly and then very, very quickly at the end, unfortunately. And it's the same thing a little bit around how does user interfaces change? So a lot of discussions are people are starting to use connected cameras more. They're starting to use smart glasses. They can also have headphones that have cameras built into them, right? If you don't actually have to wear glasses, you can just have headphones. And we talked of wireless earbuds that are cellular connected in addition to Bluetooth or Wi-Fi. And so you have this perspective then of all of these different types of devices. where they're going to have on-device compute. And they're still going to have, obviously, training, and the cloud's going to be incredibly relevant, but we actually have the compute physically on the device. And these devices need to communicate with the network. And so when we look at some of those core priorities in 6G, obviously not only capacity and downlink, but uplink and coverage. So similar to Misha's talk this morning, coverage and uplink are really important. And it's one of the reasons at Qualcomm we have a dedicated research project, and Jing Zhang's in the audience here, he's leading that, on how are we improving the low bands, the FDD bands. So we love TDD, we love MIMO, we love GigaMIMO. We also love low band FDD, when guess what? You can transmit and receive whenever you want. So I remember when I joined Qualcomm, it was an FDD world. You had your uplink band and your downlink band, and we'd learn about duplexers and diplexers and what's the separation. And you realize that as cellular's evolved, going back to the physics of propagation, the physics of coverage, these different deployment models, it's still incredibly important. So this is kind of our view on AI native design, real-time efficiency. We talk of the resiliency, but it's really the kind of staying laser focused on the reality that these devices with compute are connecting to the network. So the other thing is we're always looking, and Hemant talked a lot about this, trends. When different trends intersect or collide, and they're not always like exactly related to each other, but they're related in time, as in they start happening at the same time. And because of that, there's a preponderance of movement in a certain direction. So one of them is obviously agentic AI and how we start moving from, all this user-initiated app-based. And so if I ask, how many people in the audience have, more than 50 applications on their phone, I would expect almost all of you to raise your hands. How many have more than 100 apps on your phone? Yeah, I probably have like 7 screens, and do I have like 28 on every screen? Is it 4 times 7, or is it, all of a sudden you have so many apps, and you start realizing, is that the best way to do everything? And we give the examples of, arranging travel, and you open up your airline app, you open up your hotel app, you open up your ride-hailing app, and you're one by one opening up all these different things. Well, obviously in an agentic world, you say, hey, I need to be in New Jersey for 3 days next week, Tuesday to Thursday, propose an itinerary. And it gets back to you, what you would have individually done one by one by one. So that's kind of the agentic part, where it does introduce a turbo mode, because then what used to be serial can become parallel, right? So it does increase the intensity of things. Now, the other thing that's happening is the form factor part, that you have those pictures of, when the Pope got chosen, and there was an era before smartphones and an era after smartphones, where all of a sudden everyone's just filming everything. And you look at a concert and everyone's filming everything. And that seems like that's probably not going to be like that forever. That at some point where we love smartphones, and smartphones are, in my view, going to be around for an incredibly long time, but you're also going to introduce these other modalities as the technology moves forward. So whether it's connected earbuds, whether it's connected glasses. And so that's a good example where the form factors start changing. And then people realize it's not always going to be, cellular to the phone and then Bluetooth to the devices, but actually there's going to be more cellular connected devices because they're going to have their own independent use cases where you're only using that device. And I think the connected earbuds are a great example. Or if I'm going running on the weekend, you're just wearing your watch, right? There's a lot of examples where you don't always want to be bringing the phone around. And then you also get into some of these creative ones of how these devices can work together in cooperative communications. And then there's that other part about where is the data originating? So a big topic this morning as well, data being created at the edge. And I think this is that point around uplink. Qualcomm used to have a conference we sponsored in San Diego all around applications and augmented reality and those sort of things. We actually called that conference Uplink, K with a Q, up LINQ. And so you can Google that and you can get some fun history lessons from the early days of Qualcomm event planning. But the point is, uplink is incredibly important. So we 100% agree on that being one of the priorities. And this is the other perspective of UI and AI. So yes, this is a bit of a buzzword that AI is the new UI, but it's also interesting because as I mentioned, I do the academic collaborations at Qualcomm, and we used to kind of fund research in HCI, right? Human computer interface. And it was really interesting. We were funding some research at Carnegie Mellon, and it was interesting is how discrete, even we were looking at it at the time, right? This might have been 2009. And okay, there was an HCI track, and we talk. I focus on HCI, and you go back to your own education, and when you learned about input and outputs and keyboards, and versus the reality we live in today, Like, what are people doing on different types of screens? What are they doing, with their voice? What are they doing in all of these other modalities? So I think this is primed to have a lot of technology change, because it's obviously not perfectly matched today to how people want to use the technology, enabling them to have more hands-free interaction, enabling this sort of agentic world. So it's an interesting one where these preponderance and simultaneity of things around AI and UI, and also the reality of the operating system world and the app stores and the duality of the Android and iOS markets, there is also other types of devices that are going to come into the world where it's going to kind of change how we look at OS and app stores. So it is definitely another really big theme. And Hemant talked about this one as well, and it's this kind of perspective we often have in as we're even looking at kind of key technologies, what's more consumer focused, what's more enterprise or industrial focused. And I think it's always interesting because things like smartphones really were a consumer first market. People had phones and then they brought phones to work. And at some time, depending on people's role, their company would pay their cell phone plan. And so a phone became like, it's a consumer device, it's also an enterprise device. Whereas we would have that other hardcore scale where, robots were a enterprise device, and you have the examples that Michael Yip and others were talking about this morning on the obviously connected robots in the factory. And now we start talking about humanoids, in the home. So it is always interesting, this kind of Venn diagram view of consumer and enterprise and industrial. And you start looking, okay, what are the technologies that are common? What are the market sizes of things? So even if we're trying to, estimate the market value globally of, cloud AI, and we have these obviously $1 trillion valuations for many companies focused on the ecosystem. And the question is that value going to be realized in the cloud? Is it going to be realized in a consumer setting, or is it going to be realized in an enterprise productivity setting? And so that's one of the reasons we see so much investment in that aspect, is because people are saying, hey, if I can make my country more productive, this becomes a national priority. And there obviously big discussions in Davos on that sort of digital sovereignty and what's the ecosystem for AI like in my country. And then obviously you have the other reality that company X, whether it's an airline or another company, saying, hey, we have to make sure we're using AI to keep up and stay ahead of our competitors. So you have the ABC companies where any given company needs to use AI to stay ahead of their competitor. So it's always interesting then, you look at relative to absolute, and then the role of AI and the role of communications. So when we look at kind of the fundamental, some of the pillars of what are we driving to in 6G, what are we focusing on? So we have kind of the technology, we call it buzzword bingo, along the bottom row, where we truly have people working and teams working on every single one of these topics, because they all fit together in different ways for different applications. And then we're also really looking at what are the core gains we can get in spectral efficiency. So some of you probably know Tom Richardson, LDPC inventor. He's still at Qualcomm plugging away, designing base graphs for 6G. So it's a great example where, if I talk to someone like Roberto, who I'm fortunately still in contact with, we talk about, we need change from, turbo. We turned from convolutional to turbo. That was like a really big deal. And then from turbo to LDPC was a really big deal. And it still is a really big deal, because when we look at silicon area and doing gigabits per second, the hardware area, the AUC that Chad was talking about this morning, incredibly important. So can we have an area efficient, power efficient, low latency decode, and what's parallelizable? So this gets into a lot of interesting architecture trade-offs on the aspect. And the other thing is I know there's like many folks from different companies working on modems in addition to Qualcomm. There's always that interesting challenge of what are you doing hardware, what are you doing in firmware, what are you doing software, what's your whole kind of strategy for managing that modem. So it does get into a lot of interesting stuff. The core waveforms on uplink and downlink, we're doing everything we can to make them better, to improve spectral efficiency, and hand in hand to look at the AUC, so that when we're introducing 6G, we do want the combined area of 6G and 5G to be only a small incremental increase over 5G itself. So that does become a very significant one. How can I bring more innovation in the same area? And then it's this perspective of the network optimization and the deployment optimization. And so the other part that's kind of a little interesting is this evolution of sets of techniques. And there's a lot of really good stuff that was designed in 5G, but it was not necessarily commercialized yet. And I think we all know we're on this NSA to SA transition. The SA networks are getting deployed. We're bringing in the 5G core. But as we look to 6G, it is really our opportunity to bring in things like subband full duplex, as was discussed, or some of these more disruptive techniques that have a real challenge to the existing deployments. How can I bring this in? Can I do this in the new bands? Or can I also bring this into some of the existing bands? And I think that's like a really big focus of ours, is how do we look at technologies across the different bands? And one of the things that's going to be coming up a lot is this timeline of 6G, right? So some in the academics might not 100% know this. Certainly everyone in industry is very well aware of this, that we're already in the study item, right? So we're in release 20, 6G's, people are getting on airplanes every month and arguing about very specific things already, right? So 6G is off to the races in the release 20 standards, and then it's going to turn into the release 21 work item. And what's kind of exciting here in the United States, the current administration, the NTIA, there's a lot of focus around, hey, how can the US, not only on the spectrum side, as was highlighted this morning, but even on the use case side and the deployment side, make sure we are deploying 6G. So there is a lot of excitement around LA28. And I certainly spent a huge amount of time on airplanes going to Korea and going to Japan in the early days of 5G, when we were talking about the Winter Olympics in 2018 and the Summer Olympics in 2020, which obviously was held in 2021 in the end. But it was an interesting one. We always joke around about Olympics and Gs, but it is this thing. It kind of aligns to this 10-year cadence. And there's nothing magic about 10 years, other than it is a good integration window, going back to that cone chart on the first slide, an integration of, wow, we are using technologies fundamentally different. So how did people use social networking in 2015? Like, oh my God, to even think about that, what was Facebook like in 2015? I was not even on Facebook, thank you very much. I don't think I had Instagram yet in 2015. I did have LinkedIn. So it's a funny thing where today, things are so much different than they were 10 years ago. And that's part of that framework then that we're designing 6G for these future use cases. We're trying to say, okay, what are people going to need in 2035 when we're right in the middle of the 6G era? So if 6G gets deployed 2029, 2030, well, 2035 will be the middle of 6G. And so that's the challenge we always have, which is why we love debating internally. We love debating with others in industry. We love debating with our academic friends on some of the priorities and technologies around 6G, and start looking at, okay, FWA was a great example where people always knew about FWA. If anyone knew somebody who owned a quote unquote home in the countryside, you might have FWA, but it was a bespoke, weird solution. Someone had to make quite a few phone calls, and someone came out and installed something on a pole and brought that into your home. Versus no, the cellular bandwidth and the data rates are high enough that, yeah, you might as well just use FWA if you can. So all of a sudden it became a real market push across different operators in regions where they did or did not have wired communications. So anyways, FWA, great example. It's going to be a big part of 6G. It was a huge part of 5G, but we didn't really know it exactly when we were designing 5G of how important FWA would be. So as we're looking to 6G and we're looking at how AI is going to change the network, how it's going to change the use cases, we're always focused on some of those trials, some of the industry engagements. So we'll be at MWC in a few months in Barcelona, and MWC 26 is a pretty important marker as we head into where we're going to be in MWC 27. So if you look at 26 versus 27 versus 28, all of a sudden at that point, we're moving from the study item into the work item, and the 6G's technologies are getting, much more, I would say, solidified in terms of what's really going to be in that first release 21 day one 6G network. So a lot of the industry focuses on, we got to make sure we get 6G right so that that initial rollout makes sense to cost-sensitive operators and makes sense to that expanding ecosystem. So some of the key parts, we absolutely kind of divide and conquer and look at each frequency band differently. I mentioned a lot of the work on FDD to how can we improve coverage and how can we improve spectral efficiency in FDD bands, so stuff below 2 gigahertz. And then also the amazing C-band, the 3.5 gig, 4 gig type stuff, the high twos. That was incredibly important band for 5G. Well, the good news is 5G is a relatively flexible air interface. So 6G is going to come into that 5G spectrum. And so as infrastructure is upgraded, it's going to be able to do 6G and 5G. Obviously, the device will be multi-mode. So we call that MRSS, multi-rat spectrum sharing. So it's not so much, it's going to actually be much more efficient to do 5G and 6G in the same band than it was to do 4G and 5G. So 4G wasn't really designed with that forward compatibility in mind. People said, oh my God, I'm moving from CDMA to LTE or FDM. It's going to be a game changer. I'm kind of done. Long-term evolution. That was the name of the game. Lifetime employment, for others people called it. They kind of thought it was the end of the line. And in reality, 5G really changed a lot of things, but it didn't really change a lot of FDD. It didn't change a lot of that stuff. So there's a big opportunity in 6G. And at the same time, millimeter wave, a lot of interesting work in making sure we can continue the operators that made that investment to drive that capacity. So still huge capacity for millimeter wave. No one's leaving that on the table as we look at 6G. And so there's some of the kind of key examples on the FDD side that we're highlighting here. So this is kind of each of these individual topic, each of these 100-slide PDF at Qualcomm.com for any one of them, because it's a big focus as you're getting that incremental gain. I think a very good point this morning, good reminder on absolute versus relative, as Misha was saying, when you're trying to get that relative next 10%, after you've kind of done all the easy stuff and a bunch of pretty hard stuff, we're now trying to do relatively intricate stuff to get that next step in performance. And what do you know, 5% here, 11% there, 13% here, 12% there, you get 70%. And obviously you can't just add them all up because they're not orthogonal, but you really have to then do a lot of evaluations of all of these interrelated trade-offs. And so the other thing is we're looking at is the protocol side. So Gavin Horn, who leads our upper layer research on our team, he's always looking at, hey, are there different ways we can look at the protocol side of things? And it's interesting because if you're a hardcore physical layer person, you think like, oh yeah, I guess we need port. Yeah, I guess we do have to. Yeah, what's the error rate again? What's our? We used to talk about target, blur, block error rate. You know, how many interlaces and how are we targeting the hybrid ARQ? Well, it's actually much more subtle now when we look across applications, across QoS requirements for latency and reliability, and we start putting together, well, what's the best way to deploy this? Should I have a more kind of different design framework for how I have my target performance and my testability? So we call this kind of like AI native protocols and how can we really optimize user experience. So this is another really important type of thing you can change when you change Gs. You can do a better job at this kind of big picture stuff where you kind of take a fresh look and say, I don't know, we were doing it a pretty reasonably way before. It was very pragmatic, but maybe we can take a different framework, approach it this way. And so then when we kind of look at something like AI, this is one of our favorite slides at Qualcomm. We had a lot of fun making this slide because you can read it horizontally, vertically. It's a nice little table. So at the bottom is the physical world, right? So you go from the cloud to the basically the radio side, right? So you have your CU and your DU, and then you have your radio, your RU, and then obviously you have the air interface and the devices. So that's the bottom physical reality row, where you have more types of processor architectures. As you'll see in a few slides, Qualcomm loves CPUs, GPUs, and NPUs, and we are looking at that obviously for RAN, as well as for compute and robotics and AI and all these other applications. And then you can look up and down the stack, all the way from new service opportunities, a lot of discussion on the panel about RF sensing, new types of AI services. Well, we can also use AI to improve and optimize the network. So agents on the network side, agents on the device side, improving things like spectral efficiency, deployability, operations of the network. And then we're also bringing AI right into the air interface. So Taesang Yu's in the room. He was like leading the charge in release 18 and 19, and now driving the team as we're looking at AI and 6G on the physical layer. Like, what are we talking about in AI in RAN 1? So how are we going to use AI to really improve things like channel state feedback, channel state information, that interaction? We have a great collaboration with Nokia on cross-node channel state feedback, and with Harish's team in New Jersey. It's a great example where they do some stuff on the base station side, we do some stuff on the device side. How do we exchange that information? So putting it all together, it's a really interesting one when we say AI native. Well, what do we mean? Well, what we mean is we have a fresh piece of paper. We're designing a new G. AI has substantially improved in the last 10 years. Obviously, it's substantially improved in the last 3 years. Our ability to map AI into different types of processors has changed even more dramatically from an architecture standpoint. And then the problems we're solving for with AI up and down the stack and across the network to the device side is also a large optimization space. So we're really looking at AI in a holistic way about how we can apply it. And then the other thing we're doing is looking at things like digital twins. When we look at data and information, what are we capturing? Where are we capturing it? How can we operate kind of an end-to-end system We'll talk about multimodal. Sensor fusion was a hot topic in the 90s, a hot topic 10 years ago. It's an incredibly hot topic now, right? You look at a car and you look at the type of sensors in it. You look at the robot, you look at the type of sensors in it. You look at a smartphone. So these modalities of input become really, really important. And so then how do we use these when we look and take a macroscopic view at a city or an area of space and say, hey, we're trying to improve transportation congestion in a given city. And how can 6G, quote unquote, help with that? Well, the answer is let's take a step back and let's understand what are the inputs, what are the outputs, what are we trying to make better? And all of a sudden, it's another multidimensional optimization problem. There's going to be a lot of pragmatic engineering solutions. How you map those solutions onto physical reality, that differs every couple of years because the technology substrate is changing. And also the importance of different types of applications. Obviously, the automotive ecosystem has gone through huge change. I had great discussions at lunch with two gentlemen from General Motors. I promised I would give a great plug-in for the amazing GM product line. So if you haven't taken a fresh look, whether it's the Lyric or literally a battery-operated Silverado, so 220 kilowatt hours of battery. You know, if I thought I had a lot. I had 100 kilowatt hours in my car, twice as much. So take a fresh look at GM if you haven't recently. But it's a great example of autonomous driving and digital twins, where you realize how the car companies are approaching it substantially different than they were 5 years ago. How cities are thinking about it substantially different. Certainly how Qualcomm is thinking about it substantially differently. And I kind of mentioned a little bit on the integrated sensing and communications. When I want to get to this slide here, I know we're going to hear from Blythe Towell as well on our robotics team in a few minutes, but we kind of love the fact of this whole system 1, system 2 that Michael Yip was referring to this morning. It's pretty cool, right? We used to talk about closed loop and open loop or coarse and fine control when you go back to your quote unquote undergrad control theory, let alone more advanced stuff. And it's really interesting when you look at that humanoid space and you start realizing, you know, the challenges in terms of complexity and what are the problems we're trying to solve. And then you look at like, here we are at CWC and you look at the electrical engineering academic talent in the room and you realize every one of these challenges there's like hundreds of PhD theses in every single one of these buckets. And yet an area of humanoids is all of a sudden hundreds of billions of dollars of market opportunity. It's also a huge industrial priority in terms of the United States relative to other countries. It's a great opportunity to be looking at complex end-to-end systems. And there's the computing requirements, there's the AI requirements, and then there's the communication requirements. So Kieran Mukavili on our team is leading an effort on the communications requirements for basically humanoid robotics. And it's very interesting when we're looking at beyond the training, all of these different trade-offs. The other thing is when we kind of look at our product line, and I don't want to spend too much time going through chipset roadmaps here, but this is kind of an interesting one. So obviously I do the wireless research. This is not my team creating the IQ10, but it's pretty awesome when we see like, wow, like what are our colleagues up to? And you look at the computing, the CV processor, display audio processor. And so this is all coming in a certain platform. And we're working with Hemant on the university relations team here to get these devices into schools. So whether it's UCSD or other academic partners in the room, Texas A&M and others, we love getting these Dragon Wing IQ10s into your students' hands, into your curriculum, into your professors' hands. And they're doing some pretty amazing stuff on this, basically robotics platform, very powerful compute options. And the other cool one is our laptop. So every Qualcommer in the audience has a Qualcomm-powered laptop now. And it's pretty exciting to see, well, what's different between laptop and smartphone? And there's a lot of things where there's some commonality, and there's also a lot of differences, whether it's the operating system being Windows versus Android or other things. And it's a lot of pushing the boundaries. And we mentioned, bringing cellular into laptops, where my team comes in. We had a big end-to-end effort on that. And then last but not least, we call it the masterpiece of performance. Luckily, they didn't ask me on the naming. It's pretty cool. But this perspective of all of these different incremental gains coming together to make your smartphone substantially better than it was a couple years ago. And for those of you like me who kind of leave your old cell phones in random drawers and random parts of your house, and once in a while you lose your phone and then someone finds your like 10-year-old phone and you're like, I don't think that's it. It seems like way too thick and there's not even a case on it. So it is kind of crazy what's incremental and when you take a long enough time period apart. And so this is just an interesting one. This is literally an example of like year over year type gains in a very important large ecosystem already. So I'll kind of stop my discussion here and looking forward to other discussions. And you'll recognize people pictured in the audience here, many from the Qualcomm team. But this is another example. Anyone is curious about some of our research, feel free to check out these videos. Incredibly insightful. You'll increase the view count substantially if you click on it a couple times. So I'm just kidding. They're hugely popular. Okay. But I'm already time for a couple questions real quick. Yeah. Yes.
You must be thinking about 7G.
Exactly. You know, I mean, it's interesting when we do joke around with our Wi-Fi team because Wi-Fi kind of was able to kind of jump the number gun a little bit. So they're already on, Wi-Fi 8, and now Wi-Fi 9's coming next, but we're going to Barcelona and I heard from someone in marketing, make sure you push Wi-Fi 8. I'm like, 8? Wait, when? I think I have 6. What happened to 7, So they're going pretty fast too. But it is interesting when we say, okay, are we doing 7G because OFDM is bad? The answer will be the world 10 years from now and how we map that onto cellular infrastructure, compute infrastructure, and the device side, it will be different. And that's the interesting part of the hardware-software partitioning is changing so much. So there's a lot of misconception that when you have a new G, you drive up to the base station and you just start like hacking it down just like Fortnite. When I watch my kids play Fortnite, I'm like, what are you doing with that? Are you axing like a home? It's like, and why are you putting how big is your backpack? You're putting a lot of wood in that backpack. But it's like Fortnite, and you hacking down the base station, and you put up a whole new base station. Versus if you talk to Ericsson and Nokia, they will tell you how sophisticated the software side of the upgrade is. In addition to hardware, yeah, you need new antennas, you need new processors, but there's that evolutionary part. So I would say, yeah, absolutely 7G will happen. It'll probably happen about 10 years from now, because the world is going to be substantially different. Our toolbox is going to be different, and the problems we're going to be trying to solve are going to be different.
You didn't talk about what we call RIS or reflect arrays, and
yeah,
I hear Nokia, Ericsson, and others talking about them.
Yeah. So we're doing research on so the question was on, we joke about it because there's risks and there's like risks and lists, and Kieran was also driving that research with Osgay and others, the number of types of intelligent surfaces and reflective arrays. I think it's an interesting one when we look at deployment topology of, and even what's like basically active versus passive, right, for some of these things. So we are intrigued by that technology. We're working on it. It's true, I didn't have a chance to go in enough detail, but good question from Gabriel. Yeah.
I think we can take another question probably.
Just last one.
Yeah.
So out of curiosity, now that, robots and all that coming, we have at some point a lot of noise from Intel on the neuromorphic chip families.
Mm-hmm.
Are you guys kind of looking at this at least to support the kind of, intricate robotic movements and all that? Where you need to sit on that?
Yeah, and the person sitting right in front of you, Fatih, would also be a perfect person to answer that. And so I'll like butcher it, and then he can answer it more accurately later. No, the answer. So Qualcomm had a project really focused on neuromorphic spike-based neurons. I don't know if Blythe ever worked on it, but it was an interesting one where the hardware architectures and even GPU, CPU, NPU, our neural processing unit, and you look at, okay, what is the workload versus the hardware architecture? So that is a fast-changing field. I think Qualcomm's definitely looking at it. I would say at this time we don't have a huge effort on like truly modeling the human brain beyond scaling and evolving a lot of the current architectures. But it's a great question, and we have a big track of research also on mapping, workloads of when is a CPU better than a GPU, right? Because there's a lot of people, oh my God, it's AI, so you must run all of that on a GPU. And it's like, no, actually we have an NPU. And also a lot of AI can run on a CPU, right? So it is interesting from a latency capacity standpoint, also what's bandwidth limited versus compute limited, literally on the IO of the ASIC itself relative to the backplane and all those sorts of things. So, yeah.
Thanks, John, again for the entire.
Yeah, thank you.